The Clean Power Hour is brought to you by CPS America, the maker of North America's #1 three-phase string inverter, with over 6 gigawatts shipped in the U.S. The CPS America product lineup includes three-phase string inverters ranging from 25 to 275 kW. Their flagship inverter, the CPS 250-275, is designed to work with solar plants ranging from 2 megawatts to 2 gigawatts. The 250-275 pairs well with CPS America's exceptional data communication, controls, and energy storage solutions. Go to chintpowersystems.com to find out more.
Before the ice ages, there was a lot of dust storms for various reasons, and providing the iron, which allowed the phytoplankton, the algae, to grow and then eventually sink and sequester the carbon. So that's the #1 solution because we know it works.
Are you speeding the energy transition? Here at the Clean Power Hour, our hosts Tim Montague and John Weaver bring you the best in solar, batteries, and clean technologies every week. Want to go deeper into decarbonization? We do too. We're here to help you understand and command the commercial, residential, and utility solar, wind, and storage industries. So let's get to it. Together we can speed the energy transition.
Today on the Clean Power Hour, net zeroing the economy is actually the easy part. You know, you, my listeners, are part of the energy transition, and I have tremendous respect for all of you. And what I love about working in the energy transition is that there's so many mission-driven professionals. We all care about the environment and the future of humanity. And the good news is that the energy transition is happening. It's happening faster sometimes than we anticipated. But there's 1 trillion tons of CO2 equivalent pollution in the atmosphere that we have to remove in order to step back from the brink of climate chaos. And so my guest today is a wonderful gentleman, author, scientist, entrepreneur, who has done an evaluation of what's going on with the economy and that 1 trillion tons. And he's come up with some very interesting solutions to climate change. So I want to welcome to the show Peter Fiekowsky.
Tim, thank you very much. And audience, I'm looking forward to talking and working with you. The energy transition is so important.
The Clean Power Hour is brought to you by Dinawatts. If you're a solar PV asset manager or performance engineer, you need better data and better business intelligence. With Dinawatts digital twin benchmarking technology, you get more accurate, efficient, and faster performance measurement results. The 4th generation Dino recently completed a technical review by DNV. You can download the report at dinawatts.com. That's DENOWATTS.com. Now back to the show. It is. And it's, I think my listeners might be a little surprised to hear this message that the energy transition is the easy part, and it's going to happen, right? There's this, as we were saying in the pre-show, Peter, there's this tide of resources flowing into solar, wind, and energy storage, right? And capitalism is a real force, and when companies find markets, they create technologies, and they lean on the accelerator, and that is truly happening. We have the resources, we have the technology to net zero the economy, and the good news is we also have the resources and the technology to take that 1 trillion tons of CO2e out of the atmosphere, and we're going to be talking about that. But before we go there, Peter, tell us a little bit about your background. You have a very interesting background, hardcore science and hardcore tech entrepreneurship, but you also had an awakening of your own, which led you to write this book. The book is Climate Restoration by Peter Fiekowsky. You can just go to peterfiekowsky.com to check out the book and all the other stuff that Peter has going on, which is a lot. But tell us about your journey, Peter.
Yeah, thank you. So I started out as doing astrophysics. I just loved astronomy as a kid at MIT. I remember sitting on a sofa in one of the lounges reading Science magazine or Scientific American. This is 74 or so, and reading about global warming. And this is, you have to go back and picture the early 70s, those huge cars, and they just stank. We were pretty used to them stinking, but they really stank. This is before catalytic converters. And so the idea that we're going to have to get the CO2 back out of the air was really obvious. we were cleaning up the rivers. The rivers were getting clean. All these places we were cleaning up. And it's like, of course, by the end of the century, we'll have removed this excess CO2. And I decided that's chemical engineering. That's really hard for a physicist. And so I stayed with astrophysics. And so I'll let the smart people do the chemical engineering. Long story short, that was 74, 75. And the thing to remember is, again, for a 19-year-old, the end of the century, which was 25, 26 years later, was more than a lifetime away. Right. And so it's like, oh, it'll be taken care of. I'm going to do something fun and interesting. And, I was studying supernovas in a galaxy about 50 million light years away. No one was going to get hurt. And I say that because so many people are careful about their work in climate because they want to make sure that if I do something wrong, no one will get hurt. And that was my algorithm back in the 70s and all the way up till 2010. And I was doing a lot of volunteer work. I moved here to Silicon Valley, have a software business in semiconductor manufacturing. So I have all the normal things, a family, and I got 3 grandkids now. So I was doing volunteer work on advocating for hunger and poverty issues. So I said, what's really hard is how do you feed everyone?
Right.
Because and so that was my big focus for decades as a volunteer. And we got funding to vaccinate the world's kids and vitamins, all these things that made huge differences. By 2010, that was clearly leveling out, and things were beginning to get worse because of the climate. And so I went back and I thought, 35 years ago, it was very clear what we had to do. Let me go back and stop ignoring the climate and see how they're doing. So I go to my friends at MIT. I went to Dr. Jim Hansen, who is on the board of one of the organizations I work with, and said, hey, how's it going getting the 1,000 gigatons of CO2 out of the air? And it was just silence. They said, well, we're not working on getting CO2 out of the air. The UN says we have to reduce emissions. I said, well, it's too late for that. We're already 40%, 30% above anything humans have ever survived. And they said, yeah, that's true. But, the UN says we have to reduce emissions. And so that was how I got into it. It was a very reluctant time, a painful time for me, because I did not want to lead a movement. I had a software business, I had a family, and all was well. But I'm committed to our children having a historically safe climate that we know humans have survived. And that wasn't on the agenda.
This reminds me of the saying, we are the ones that we've been waiting for. It's very convenient to think that someone else is going to solve the problem, so to speak.
Yeah.
But we're all responsible. We have to acknowledge that we have the knowledge and information and resources to solve the challenge. The challenge is real. There are significant forces that continue to try to convince society that there's not there with climate change. The oil and gas industry is front and center in this. They're pouring lots of resources and political power into keeping the burning going, right? And the result is, CO2 in the atmosphere, the levels are now above 420 ppm. They're going up, right? Even though the rate at which they're going up is starting to slow a little bit, right? We are starting to put on the brakes globally. You have to think about all the countries in the world that are still developing, right? And we here in America have, we're 5% of the population, but we're a much larger share of the problem per se, right? And so we have a fiduciary responsibility, I like to call it really, to do our part. And the answer is surprisingly simple. As far as the energy transition goes, as Jigar Shah likes to say, deploy, deploy, deploy. Solar, wind, batteries, and other forms of energy storage. Okay, there's a plethora. Look at our back catalog. Go to cleanpowerhour.com. Check out our back catalog. We did a wonderful series on all kinds of energy storage technologies in the last 6 months. And they are many, and they are using today's technologies. Okay, so it's not some future fantasy. And no, nuclear power isn't the answer because it just takes too long to develop nuclear power. Of course, the technology works. We've been using SMRs in submarines for decades, but they're not the answer, unfortunately. The answer is surprising, though, and I love this paradigm that you created, finding solutions that are permanent, scalable, financeable, okay, and then here now, right, like practical. So I want to start with, tell us about that journey on identifying the solutions that you have identified in Climate Restoration, the book that you wrote in 2022. And it's a very accessible book. It's written for lay people. And I would encourage all of our listeners to check this book out. It is my favorite book for 2023. I just discovered it thanks to my father, Peter Montague, for bringing it to my attention. But I think it's very sensical, but not obvious, right? The solutions that you've identified are somewhat off the beaten path. Some of them are no-brainers, like synthetic limestone manufacture. I think most energy professionals know that we could capture CO2 out of the atmosphere and make limestone, and of course that's going to stay as stone for a very long time, and thus it's a permanent solution. Unfortunately, there are other forms of carbon capture, for example, CCS, right? Compressing it into liquid CO2 and then pumping it into the Earth's crust. It might work, but there's a lot of uncertainties about that. And we now have 60,000 miles of CO2 pipelines planned for the United States. And they're putting it in places like my home state of Illinois, where they're going to put it in the ground and pray to God, basically, that it stays down there. And if just a fraction of it leaks out, then we have the same problem. So anyway, tell us about your journey to identifying the solutions, and then we'll get into the 4 solutions that you've identified.
Perfect. Yeah. So once I started getting serious about the climate, the first thing, of course, was to figure out, this is for me around 2012, how do we transition from fossil fuels to clean energy? And you mentioned Tony Seba, and there was very clear, it became clear 2012, 2014, 2015, 2016, very clear that the energy transition was going to happen. And in the book, given that your listeners are largely energy people, my chapter 2 summarizes a lot of the work that Tony Seba did. And I think almost everyone here listening is clear that we are going to be mostly electric vehicles in 10 years. Most of our energy is going to be solar and wind. I would say the nuclear differently. I mean the same thing, but I say it differently. That there's a niche for nuclear, and the nuclear will fill that niche.
Okay.
And because it's roughly 10 times, I think the IEA says 9 times the cost of solar. Right. Well, there are places where solar doesn't work. So for them, and if there's no wind, they'll use nuclear. So, and that's fine. But the point is that's happening. And so the thing I invite people who are working on the energy transition to do is to make sure you have a lot of fun doing it. It's like, we don't need to bash the nuclear industry. We can welcome them in. There is going to be a niche for them. As you said, the economics are very cut and dried. They're not going to build a new nuclear plant in California because we have lots of sun and wind.
Right.
That's fine.
Maybe Antarctica or something like that. Although
Right.
there is lots of wind in Antarctica, there's not a lot of sunlight, but there's a lot of wind and
Right.
wave energy. But anyway,
So then once you get that the energy transition is essentially a done deal, and we want to make it a beautiful done deal. I love the picture in your background there of the solar panels on the hillside. Then you say, okay, good. If that's a done deal, let's figure out the next step, which is how do we get the CO2 back to sustainable levels? And the first the first step there is to answer the question, what's the level that we want? And that was the biggest breakthrough. Was it actually happened at a climate conference for me in Marrakech. And you can just imagine the bazaars in Marrakech. And so there was a bishop who had a dinner who invited me and about 10 other people. And he said, we're going to talk about the morality of climate. And as a physicist, I rolled my eyes and thought, oh, morality. I'm into solid things, but I'll learn something. I'll at least meet someone here. And it changed my life, and it perhaps changed life in general, because for the first time, I saw that the climate was an issue for humans, that the rest of the planet, besides humans, would just roll with the punches. No big deal. It's happened a gazillion times and will happen a gazillion more times that the climate changes radically. For humans, we want to restore the climate. We want the climate such that humans will survive. And bing, that tells us we want to restore the CO2 levels that humans have historically survived, which is anything below 300 parts per million. And that's the level we passed last time in 1920. And then before that, it was 300,000 years ago. Was still Homo sapiens, right. And CO2 was at that level for 1,000 years or so. Anyway, so 300 parts per million, the level it was 100 years ago. So, okay, good. We now know what the goal is. Oh, how do we get there? We have to remove, as you said, 1,000 gigatons of CO2. Cool. And again, I love that we have a fairly engineering audience here, because I think they'll just get the feel. Okay, good. 1,000 gigatons. Oh, by when? We debated it, and 2050 is what landed. It's like, let's target 2050. And again, this is really serious. Like, why did President Kennedy say land a man on the moon by the end of the decade? Because it felt right. And so that's the meaning behind 2050. And I think we'll do it by 2040, actually, but don't tell anyone. And so then, okay, good. You do the math. You have to get 50 gigatons of CO2 out per year, in addition to anything that you put in, because the energy transition is going to take a few decades. But you do the math. It comes out to about 60 billion tons a year we need to pull out on average. And we start in 2030, so give us 6 years to build up, which is actually reasonable, you'll hear. And then 20 years of removing it. Okay, good. That's an engineering plan. And then again, a lot of your listeners do projects. You figure, well, we need a plan A and plan B. So we knew we had to have at least 2 and hopefully 3 viable alternatives, because it's too important to only have a plan A. And so we knew that going in, there would be 3 alternatives. And you asked me before the show about, what alternatives did we have to throw away? As soon as I knew what the answer was 50 billion tons a year, I had a request from Congress to give them some language for a climate bill. What you want for climate restoration, and I used that as an excuse, carbon removal, and that was a fun conversation. They had never gotten together again before that, and came up with, I think, 7 different methods. And most of them were what's called direct air capture. And that makes sense, because that's what we've been doing in submarines, right? In the submarine, you have people breathing and perhaps little motors producing CO2, and you have to remove the CO2. And there's chemical ways of doing it, ammonia-based and so on. And just so you can picture, again, I love having a technical audience. CO2 is acidic. And so if you have a basic thing like ammonia, it'll absorb the CO2. It's really not much more complicated than that. Anyway, so most of the methods we looked at were derived from what we had in submarines. And of course, that was right after the Apollo program. So we had spaceships. And so we have to throw those away, though, because they're just too freaking expensive. Now, I stuck with that. Everyone knew it was going to be $1,000 a ton back from decades ago. And I resisted it along with everyone else. I'm sure we can get it to $100 a ton. No, it's still $1,000 a ton 10 years later. too expensive to scale up to if you multiply $1,000 per ton times 60,000 tons, that's $60 trillion. That's almost the whole global GDP, right? That's not going to happen.
Right.
So we have to throw a whole slew of direct air capture methods. Now, they're still in business because they're producing CO2 that the oil companies need for manufacturing and for pumping underground to push out more oil. But that's a whole different topic, which we don't probably want to go into. It took a long time. It took almost 3 or 4 years of talking to everyone before I realized that nature had solved the problem. And nature's solutions weren't on that list that we did with the 8 scientists. So if you think about it, our planet has had ice ages periodically for millions of years.
Right.
And the last one was just 12,000 years ago. Right. So, Jesus was at 2,000, Moses was about 5,000 years ago, and the last ice age was 12,000. This is like really recent, the last ice age. How did the Earth remove the 1,000 gigatons to cool the planet, which is what we need to do? We're going to remove 1,000 gigatons to get back to pre-industrial. So how did nature do it? Well, nature did it by photosynthesis in the ocean. We all know about photosynthesis on Earth. We have crops and we have trees. Yep. But I think we all know that those trees and crops, they last a year, or trees, a few decades, and then they die and rot or burn.
And that basic chemistry is you suck in CO2, plants breathe in CO2, and they combine CO2 with water to make carbohydrate, otherwise known as biomass or wood or plant material, right? And then they breathe off oxygen, which is something that we breathe. So it's a nice symbiosis that plants have created, something that's been around for millions of years, and so it is tried and true technology, so to speak. So let's continue that conversation.
Good, yeah, and so it's photosynthesis in the ocean that nature uses because. As we said, on land, it's short-lived, a year, a few decades, maybe 100 years in a few cases. On the ocean, when plants die, they sink, or the animals that eat them sink. And there's almost no oxygen in the deep ocean, and so it doesn't rot. And that's how ice ages happen, is you get a lot of photosynthesis at the ocean surface, and then the biocarbon sinks. Most of it does not go to the bottom. Only a little bit goes to the seafloor. Most of it is suspended. They call it as dissolved organic carbon or dissolved inorganic carbon, and just is suspended in the ocean. And then at the end of the ice age, the currents will change, oxygen will become available, and then it'll rot and come back out as CO2, warming the planet again. We'll have to figure that out. But the trigger for getting that photosynthesis at the ocean surface at the level needed is a micronutrient, iron. That is, if you think about it, and why isn't the ocean all beautiful green, like a field? Right. Is that there's lots of water and sun. And if you swim in the ocean, you can tell there's all sorts of nutrients. Of course, there's salt, but there's all sorts of minerals. The mineral that's missing is iron. And just like humans and your garden need iron, the ocean needs iron. And the reason the ocean is mostly blue is that the iron tends to sink. It doesn't tend to dissolve well. And the only source of iron in most of the ocean is dust storms blowing dust with iron from the land over the ocean. And before the ice ages, there was a lot of dust storms for various reasons, and providing the iron, which allowed the phytoplankton, the algae, to grow and then eventually sink and sequester the carbon. So that's the number one solution, because we know it works. We can talk a little more about it. Just as I said, we need to have a plan B as well. And the other thing that nature does is limestone. 99.9% of all the carbon on our planet now is sequestered on the seafloor as limestone from hundreds of millions of years, almost 1 billion years of the growth of plants and animals in their skeletons and shells. They sink to the seafloor. Those bones, shells and bones are essentially limestone, calcium carbonate, and that also can be duplicated. And we'll talk about that in a second. What's cool about limestone is by weight, it's almost half CO2. It's calcium carbonate. If you know the chemistry, you can see it's 44% CO2. And if you think about an oyster and an oyster shell, you can see it's not complicated, right? This little oyster makes this beautiful oyster shell, which is pure limestone with a different crystalline structure than what's used in your buildings or your concrete. So those are the plan A and plan B. There's others we may have time to talk about. What's very cool about the first one, plan A, is to make it happen is insanely easy. And it basically, you're duplicating dust storms. The amount of iron required is about $10 million a year worth of iron sulfate. And that's enough for the whole planet to sequester 60 billion tons a year of CO2. It's mind-boggling. Like, you mean $12 million of iron? Well, you have to distribute it, so call it 100 million or maybe 200 million because you have infrastructure and testing and safety and so on. But again, we're talking definitely less than $1 billion, and probably not much more than 100 million.
The Clean Power Hour is brought to you by CPS America, the maker of North America's #1 three-phase string inverter, with over 6 gigawatts shipped in the U.S. The CPS America product lineup includes three-phase string inverters ranging from 25 to 275 kW. Their flagship inverter, the CPS 250-275, is designed to work with solar plants ranging from 2 megawatts to 2 gigawatts. The 250-275 pairs well with CPS America's exceptional data communication, controls, and energy storage solutions. Go to chintpowersystems.com to find out more. Let's talk a little more about this, the iron fertilization. So it's called ocean iron fertilization, or OIF. Just Google that and you'll see. There's been some pilot studies on this. And the theory is that iron is a limiting factor preventing more growth of plants and animals that grow shells, and like diatoms, for example. They're microscopic organisms that are the bottom of the food chain. One of the problems with global warming is that as CO2 levels go up in the atmosphere, the ocean gets acidified, and those creatures can no longer make their shells. But how do you distribute the iron? I don't doubt that iron is super abundant in the Earth's crust, but it sounds like quite a problem just to get it out there. Is this by airplane or ship, or how are we going to pump the iron and distribute it into the ocean?
Yeah. So iron is one of the most abundant elements on the planet. And the amount needed is just a few piles of dust from the steel mill. So the availability of it is not a problem. It would be like 50,000 tons a year, 60,000 tons a year. So that it's probably 10 train car loads. I just guessed that.
Okay.
But very little iron required. And so then your question is, well, how do you get it out to the right place at the right time? And the best answer at this point is by ship. You can do it by air, and that may ultimately be the way to do it. But the advantage of ship is, of course, they use much less fuel, and you can put exactly the right amount at exactly the right place. If you distribute it by air, like a dust storm, nature does that, but it's pretty random, and most of it probably doesn't go to the right place at the right time. The ship, you can do a bullseye, and that way you're assured of less unintended side effects.
And so you're targeting areas of upwelling where there's already like nutrients coming up from the deep sea. This tends to be near the coastlines, which tend to be very productive areas, right? Which is very convenient for us because that's where we are. 70% of the human population is within a few miles of the coast. And then harvesting the bounties of the sea, so to speak, the fish and other sea life and plant life.
Yeah.
Seaweed permaculture is also on your short list. So there's
Yeah.
two forms of ocean, augmenting ocean growth, so to speak, on your list. Does the seaweed permaculture angle, does that play in, with this iron fertilization?
Yeah. Well, so first of all, the iron fertilization would normally be done 100 miles or more out to sea. Because near the coast, you always get runoff from the land, and there's plenty of iron in the water.
Okay.
The concentration of iron in the deep ocean is a millionth what it is in the coastal areas. So like it's a big, big, big difference. And yes, typically what's being planned is to add the iron dust to the ocean in eddies. They're called mesoscale eddies, 100 miles in diameter. And because it's an eddy, it keeps the iron in one place for a whole bunch of months. And that allows the ecosystem to go through its normal arc whenever it's like with growing plants, growing a crop on land, because really it's almost identical to farming. And you want the farm to go through the whole season from beginning to end. So they'll do it in an eddy where it'll last, the fertilization will last 4 to 8, 10 months. And then you asked about the permaculture, the seaweed permaculture. That also would be done everywhere, mostly in the deep ocean, because the idea there is just like the iron fertilization, which grows microalgae. The seaweed is macroalgae, so it's large algae plants, but they need to sink to the deep enough where there's no oxygen. And so that's going to be, at least 100 meters, at least 300 feet deep. And so, and it varies depending on where you are in the ocean. And so, that is viable. That's our plan C. And, what's changed in the last year and a half since I finished writing the book is that the climate, of course, has gotten much worse. The wildfires, the droughts, and the floods and the storms have gotten much worse. And so I'm now focusing really on just the top two solutions. I'm the limestone and the permaculture, the seaweed, I'm encouraging and supporting, but both of those require a lot more infrastructure and will take more years and decades to get to scale. So I'm focusing on the iron fertilization, which we could get to scale, totally to scale by 2028. And then the one we haven't mentioned yet, which is methane oxidation, which we also could get to scale by 2028.
And so real quick, it occurs to me that we already have a massive fleet of ships plowing the seas. We could just put some iron powder on all of those ships. These are fishing ships, these are passenger vessels, and of course, container ships that are moving stuff around. It doesn't seem like a big stretch to just ask them or mandate them to start adding this to their journey.
Right. And that may happen, in the short term. We don't want to do it quite like that, because for the sake of sanity, we want to make sure it's done safely. And so we want to do a few selected spots, carefully. Because if you ask the commercial ships in the short term to do it, the crew aren't going to be trained on the pros and cons and how to do it carefully. In the long term, that may happen. In the short term, it'll be ships. But the tests that have been done on the iron fertilization, some of them are done with just old fishing ships, which cost $1 or $2 million. So it's not a big issue.
And is there a potential downside with the OIF solution?
Physically, no. That is to say, in the physical universe, nature has been doing it for many millions of years. And so the nature of it, and we're doing the exact same thing that nature does. It's just, we're just, rather than doing a wild dusting of everything, we're using just the minute amounts of iron sulfate. And so it's much less quantity. In the 13 scientific tests that have been reported, there's been 0 reports of any bad side effects, which is not surprising. As I said, nature has been doing it. And 1991, Mount Pinatubo erupted and put a lot of iron-rich dust in the South China Sea, near the between the Philippines and China, and created so much phytoplankton growing that the CO2 level was flat the following year, 1992. If you look at the Keeling curve, the CO2 curve, it goes up steadily, flattens for 1 year, 92, and then goes back up at the same rate. And all the evidence is that 20,000 tons of CO2 that was removed were related to the iron fertilization. We can't prove it because there weren't any satellites up then that that recorded the chlorophyll, recorded the greenness of the ocean, unfortunately. But so all we know is that worldwide fishing increased in the years following. It went up about 15 to 20%, and fish catch increased a lot, and was steady. Went up after Mount Pinatubo and stabilized again, and and the CO2 level went down, and that CO2 never came back. So it's been done a lot. Is a point.
Okay, so the four solutions that you highlight in your book are ocean iron fertilization, seaweed permaculture, synthetic limestone manufacture, and enhanced atmospheric methane oxidation, EAMO. Yeah. Now we're going to drill down on that, on EAMO. Why enhanced atmospheric methane oxidation? Why is that so important?
What got me into the methane was because I figured methane's only 19% of global warming. And so let's worry about the big 81% first. And once I realized that we had three different methods to get the CO2 back to historically safe levels, I danced the jig and then realized that the methane was there. And the big problem with methane is what's called the methane burst. And in the Arctic area, you have permafrost, which is where the water in the ground is so cold it never melts. But it's warm. The Arctic is warming up 3 times faster than the rest of the planet. And so that permafrost is melting. And in that ground, there's thousands and almost millions, almost a million years of biomatter, plant matter that's been accumulated over the years. And when that melts, it essentially ferments and turns into methane. And historically, the last time our planet warmed up like it is now, which was about 54 million years ago, we lost the Arctic ice cap. You and I weren't alive 54 million years ago, but our planet was. So our planet lost the Arctic ice cap because the planet warmed up, and there was a burst of methane from the melting permafrost, especially under the shallow ocean. There's a lot of continental shelf in the Arctic Ocean, and that when sea level goes up and down, that continental shelf gets a lot of plants on it, and mostly moss and so on. And that melted, and that burst of methane heated the atmosphere so quickly that about 1/3 of the species on our planet went extinct. And we want to avoid that. Yet we're on the same path. That is, by in the next 15 years, almost certainly our Arctic ice cap will have fully melted during summertime. And so the enhanced methane oxidation allows us both to cool the planet by 10 or 20% as we reduce the methane level. More importantly, if the methane burst starts, and it's actually started, if the methane burst gets bad, then we can oxidize it before we lose species, and especially before we lose a harvest and lose our civilization. So it's mostly an insurance policy.
It strikes me as a very difficult problem. You think of the northern the northern part of Russia and Canada, right, where this permafrost lies. It's a vast area, and so the methane is just going to be bubbling out of the tundra. How do you attack the methane? What is the methodology?
Right. I love your description. That's how I walked into it, saying basically, "Oh my gosh, what do we do?" it turns out that if you ask what would Mother Nature do, it took a while. It took me about 6 months of panic. I said, "Oh, what Mother Nature does is, if you know about methane in the atmosphere, you know that it has a lifetime of 12 years, which is equivalent to a half-life of 8 years. It just oxidizes in the atmosphere. The sunlight and various chemicals cause the methane to oxidize. Methane is the gas you use in your stoves and so on to heat your house and cook. And so this enhanced methane oxidation simply is designed to double the rate that nature oxidizes the methane in the atmosphere. And so rather than having to do something in the Arctic, which is impenetrable, and you never know what politically is going to happen in Russia, of course, then if you just wait a few months for that methane to drift on south, then you can oxidize it in the atmosphere near the equator where you have a lot of sunlight, because these reactions are triggered by sunlight. And so that's the enhanced methane oxidation. Very specifically, it uses iron chloride, which is a chemical widely used in water purification, and the chlorine and the iron in the iron chloride, it's aerosolized, and nature does this with in the dust storms that come off the Sahara. What makes the Sahara dust pink is iron, and sometimes that iron from the dust will find chlorine from the sea salt and sodium chloride as it blows across the Atlantic Ocean, and it turns into iron chloride. And those chlorine atoms, if it's hit by sunlight, will knock off, and then that chlorine atom, like chlorine bleach, will oxidize methane. And so that's a natural reaction. And then we've demonstrated that it can be done at scale. Right now we're in the middle of lab experiments, but everything is going well.
So it's just a matter of pumping iron chloride into the atmosphere. Is that what you're suggesting?
Yeah.
Okay.
Yeah. And it's not very much. It's 100,000 tons or something like that. So
Okay.
it's a lot, but it's not very much.
Okay.
And so the trick is this. What's really cool is that the chlorine reacts with methane almost 10 times faster. I don't know, 10 or 15 times faster than the usual things. Mostly it's OH radicals. What doesn't matter what those are, which oxidize the methane. This is so fast that we only need 1 or 2% of the air over the ocean in order to produce the result that we need to cut levels in half and ensure our children and grandchildren that if the methane burst gets bad, we'll be able to oxidize it before it causes extensive ecosystem damage.
Mm. So let's talk about the cost of this. You've come to a surprising conclusion in your book that all of this is going to cost somewhere between $1 billion and $2 billion a year. Is that right?
Yes. Yeah. In fact, since then, it looks like it'll be less than $1 billion in total. Not that, both of those numbers are very close to zero relative to the global economy is $100,000 billion. So
right.
This is
$100 trillion.
Right. So about 100,000th of the size of the global economy.
And how do you propose humanity kind of pivot and really start to shine a light on this, and then focus these resources in the right areas? I mean, it's a trivial number in relation to the global economy. A single billionaire like Elon Musk could solve the problem.
Yeah.
Why don't they do that?
That's where these interviews come in, is that there's a historical problem we're up against. And historical problems are pretty easy to solve once you solve them. The historical problem is in 1990, and in the 80s and 1990, was clear we had a climate problem, and the UN decided that the solution was to stabilize greenhouse gas levels, stabilize CO2 levels. And if you remember the climate in 1990, and almost no one does because it was just the climate. Right? There was nothing to see. stabilizing it made sense. Well, at this point, CO2 levels are already 40% higher than humans have ever survived long term.
Mhm.
And so it's been 30, 35 years. And the goal we made in 1990 is no longer valid. We've got to say restore and stabilize. And so what we need is for professionals, everyone, to say that we need to update the UN goals to today's situation, which is and call for restoring and stabilizing. On my website, peterfiekowsky.com, you can endorse the resolution. There we go. You can endorse the resolution, which was passed in California last month, which says that California is committed to restoring the climate for future generations. And if you go up on the top, you can see the tab for endorse the resolution. So we had the resolution has passed in California, and we're now looking to have it introduced into the House and the Senate. Once the House and Senate discuss the idea that we want to give our children a historically safe climate, which is a new idea, then I think the Biden administration will adopt it, and the UN will quickly adopt it because it's a no-brainer. It's just everyone wants to be second or third, not first. So the listeners can sign on to the resolution here. I talked to my local representative, and her staffer said, listen, get some sign-ons, get some endorsements, and then we'll introduce it into Congress. So sign on. If you know someone in an environmental organization, Sierra Club, 350.org, any of those, have them sign on and mention that they're from that club. If they're an official in the club, we especially need endorsements from environmental organizations saying that this organization actually supports the idea of giving our children a historically safe climate.
So go to Peter Fiekowsky, that's Peter, FIEKOWSKY.com, and then you'll find information about the book at the landing page, and then go to endorse the resolution. This is a call to action to get Congress's attention that there is a concrete solution to the problem per se, and it's cost effective. And then this will lead to what, Peter, if we're successful? Because you also have something called the Grandparents Fund, which is a philanthropic initiative, right? You've started a foundation, and you're raising donations for the Grandparents Fund. But how do these two play together?
Yes. Well, with the resolution, both the UN and, as you mentioned, Elon Musk could fund it. He actually knows about it in the past. I'm told that he has funded iron fertilization back in around 2005. But when these are endorsed, then it makes it easier for someone of his level to stick his neck out. So that's the main thing. The Grandparents Fund similarly allows people not to go beyond just signing their name and say, listen, I'm willing to put in $10 a month, $100 a month, $1,000 a month, $1 million a month. If any of your listeners are at that economic level, they can put in $1 million a month. Pretty clearly, that would be enough to fund all of climate restoration right there. So it's crowdfunding.
Right. And then I guess are there companies that are dedicating their lives to this iron fertilization and enhanced methane oxidation?
There are two startup companies working on it. They're both very small in the ocean fertilization. The one company that's established is called OPR World, Ocean Pasture Restoration World. Very small, just one or two people still. And then there is in methane oxidation, a company that I helped establish several years back called a Blue Dot Change. And they're both looking for investment and support. I'm designing a nonprofit to do the same thing, because what I'm finding is that environmentalists and scientists are much more comfortable if the climate restoration is done by a nonprofit, which is accountable to the public, whereas a for-profit is accountable to the shareholders. And so that's a different kind of a game to play.
In our last couple minutes together, Peter, there are a lot of different solutions out there that people hear about. One of the myths is, well, why don't we plant 1 trillion trees? Surely you've done the math on some of these solutions. What were the solutions that got nixed off your list of obvious answers that surprised you the most?
Oh, well, as I mentioned, the first one was the direct air capture, but that was a quick strike it off the list because it's so expensive. The 1 trillion trees never made it onto my list because I know that trees die after a few decades. And so that's just not permanent enough. And then biochar, where you basically make charcoal from any kind of agricultural waste. It's very good, but it's fairly expensive, but it's limited because there's just not that much agricultural land, and getting people to do something expensive is difficult. So we set that aside. There's another one, bioenergy and carbon sequestration, where you do things like corn ethanol, and then you take the CO2 that's produced and bury the CO2. Again, it's fairly expensive, and you're competing on land against farming for human purposes. And so it's possible, but again, just too expensive to scale up. There's a new one which is getting a lot of interest, but again is not viable. That's the ocean alkalinity enhancement. And the idea there, as I mentioned towards the beginning, that you capture CO2 by using something alkaline. That CO2 is acidic. If you have something alkaline, it'll absorb the CO2. And if you dump alkaline rocks into the ocean, then you can absorb a lot of CO2 from the ocean and reduce ocean acidification. The problem with it is if you want to make a climate size difference, you need 50 billion tons of CO2 a year. That comes up to 100 billion tons of rock. That's twice the amount of every kind of mining in the whole planet. That's 10 times the amount of coal every year. And that's just not practical. But it's an exciting idea. The government's putting a lot of money into it because the government is, and mainly because we haven't convinced the government that our goal needs to be a 21st century goal of restoring the climate, not the 20th century goal of stabilizing it. And that's where your listeners can make a difference.
The Clean Power Hour is brought to you by Dinawatts. If you're a solar PV asset manager or performance engineer, you need better data and better business intelligence. With Dinawatts' digital twin benchmarking technology, you get more accurate, efficient, and faster performance measurement results. The 4th generation Dino recently completed a technical review by DNV. You can download the report at dinawatts.com. That's DENOWATTS.com. Now back to the show. Excellent. Well, check out all of our content at cleanpowerhour.com. Give us a rating and a review on Apple and Spotify. And most importantly, tell your friends and colleagues about the show. That is how more people will learn about the show and ultimately get involved with these solutions to climate chaos, which are just staring us in the face. We have the technology. We just need to get busy putting a fraction of our resources into these technologies to step back from the brink of climate chaos and create a safer, healthier future for humanity. I want to thank author, scientist, and entrepreneur Peter Fiekowsky for coming on the show today. Thank you so much, Peter.
Oh, thank you, Tim. This was a pleasure. And listeners, thank you for the work that you've done. And thank you for the work that you're going to do promoting the future of the climate restored.
I'm Tim Montague. Let's grow solar and storage. Take care. Hey, listeners. This is Tim. I want to give a shout out to all of you. I do this for you twice a week. Thank you for being here. Thank you for giving us your time. I really appreciate you and what you're all about. You are part and parcel of the energy transition, whether you're an energy professional today or an aspiring energy professional. So thank you. I want to let you know that the Clean Power Hour has launched a listener survey, and it would mean so much to me if you would go to cleanpowerhour.com, click on the About Us link right there on the main navigation. That takes you to the About page, and you'll see a big graphic, Listener Survey. Just click on that graphic, and it takes just a couple of minutes. If you fill out the survey, I will send you a lovely baseball cap with our logo on it. The other thing I want our listeners to know is that this podcast is made possible by corporate sponsors. We have two wonderful sponsors today, Chin Power Systems, the leading three-phase string inverter manufacturer in North America, and Dynawatts, a performance monitoring platform for utility scale solar. So check out CPS America and Dynawatts. But we are very actively looking for additional support to make this show work. And you see here our media kit with all the sponsor benefits and statistics about the show. You know, we're dropping 2 episodes a week. We have now over 320,000 downloads on YouTube, and we're getting about 45,000 downloads per month. So this is a great way to bring your brand to our listeners. And our listeners are decision makers in clean energy. This includes project executives, engineers, finance, project management, and many other professionals who are making decisions about and developing, designing, installing, and making possible clean energy projects. So check out cleanpowerhour.com, both our listener survey on the About Us and our media kit, and become a sponsor today. Thank you so much. Let's grow solar and storage. The Clean Power Hour is brought to you by CPS America, the maker of North America's #1 three-phase string inverter, with over 6 gigawatts shipped in the U.S. The CPS America product lineup includes three-phase string inverters ranging from 25 to 275 kW. Their flagship inverter, the CPS 250-275, is designed to work with solar plants ranging from 2 megawatts to 2 gigawatts. The 250-275 pairs well with CPS America's exceptional data communication, controls, and energy storage solutions. Go to chinpowersystems.com to find out more.